So Gauss's law basically gives us the result of divergence of the electric field in a region. Okay, so if you consider, so this is just recapitulation of what we have already done. So if you consider the electric lines of force and a surface inclined at an angle theta to the lines of force, then the dot product of the electric field with the area vector of this surface that is inclined at an angle through which the lines of force are passing, that is known as the flux. Okay, so phi equal to Ea cos theta is the flux. Okay, so we can write phi, the flux, equal to E dot A, the dot product between electric field and the area through which the lines of force are passing. So the strength of the electric field is proportional to the density of field lines, and the flux through a closed surface is a measure of the total charge inside. Basically, this is what Gauss's law tells us. It gives us the fact that the flux of the electric field through any closed surface is equal to the measure of the total charge inside. So we are dealing here with closed surfaces enclosing a certain volume in which a charge is there, a charge or a charge distribution or several charges. Okay, so the statement of Gauss's law is, in SI units, the surface integral of the normal component of the electric field over any closed surface is equal to the total charge inside the surface divided by the free space permeability. This is the, the language of this is the language of the statement of Gauss's law, the quote unquote language. Okay. Now, so if you want to state this law mathematically, then this is the statement, that closed surface integral E dot n cap ds equal to q by epsilon naught, where q is the enclosed charge. So we saw what is the insight of this law? What does it mean? Suppose we have an isolated positive charge and we have number of lines of force passing coming out from it. They are all in radial direction. So if we draw a spherical surface surrounding this isolated charge, remember a spherical surface, so we are talking about three-dimensional surfaces over here. Okay, so the total surface area of this particular surface is 4 pi r square. So if the number of lines of force coming out from Q is n, then the number of lines of force passing per unit area of this surface is n by 4 pi capital R square. Now if you take another surface at radius twice r from that charge Q, then the area of this surface is 16 pi r square. So number density of electric field lines through this outer sphere, through the green sphere, will be n by 16 pi r square. So 1/4 of the density of lines in the first case. So definitely, since electric field is a measure of the density, since the density of lines of force gives us a strength, measure of the strength of the electric field. So definitely strength is weaker at the outer surface than in the inner surface. However, if you calculate the field, the magnitude of the field from the charge Q at a distance r, it is Q by 4 pi epsilon naught capital R square, and at the distance twice r is Q by 4 pi epsilon naught 2r whole square. So the flux, that is field into area, product of the field, electric field, and the area through which the lines of force are passing. If you take that, in the first case, it is Q by epsilon naught. In the second case, it remains Q by epsilon naught. So even though the strength of the electric field decreases as you move away from the charge, the flux, that is a quantity that depends only on the charge and not on the distance. So the flux is a quantity that remains constant even if you move further away from the electric the charge that is producing the electric field, and it depends only on the magnitude of the charge that a certain area encloses. Okay, so that is basically the essence of Gauss's law. So I will not go through the proof of Gauss's law, I have explained in detail the steps to be followed. Just remember that we have a surface, closed surface of any arbitrary shape. S is a closed surface of any arbitrary shape, encloses a volume V, and within it we have a charge Q. Okay, so if you consider an area ds at the surface, which is at a distance r from that charge, so electric field is along r, and if the angle between E and ds is theta, then the flux is E ds cos theta d phi, the flux through the small area ds. So the total flux to the entire surface will be the integral of d phi, and it is given by integral E dot ds. Okay. In this particular case, we have one charge, so electric field is q by pi 4 pi epsilon naught r square at that distance r, so that we get phi equal to this quantity here, q by 4 pi epsilon naught integration ds cos theta by r square. And I told you this quantity is the integration of the solid angle d omega that is subtended by the area ds at the position of the charge q, and the total integration of a solid angle about a volume is always 4 pi, and I explained this also. So this is the solid angle for this particular infinitesimal area. So if you integrate over the entire surface, you are basically spanning the entire three-dimensional space, and so that value comes out to be 4 pi. Okay, so finally we get that phi is equal to q by epsilon naught, or in other words E dot n cap ds is q by epsilon naught. So this is Gauss's law for a single charge. And then I told you, you can't stop here. So you have to imagine that there are, the next step is that you imagine there are several such charges enclosed within that area. So the total field by principle of superposition is the vector sum of all the fields produced by each of these charges. And then therefore E dot n cap ds integration is, you write E as the sum of the individual fields produced by the individual charges, and then you can separate the integrals, and for each integral you apply Gauss's law, and you get q1 by epsilon naught, q2 by epsilon naught, etc. And so, okay, and so finally E dot n cap ds therefore is the sum of all the charges, all the discrete charges divided by epsilon naught. Okay, so q enclosed by epsilon naught, where capital Q is q enclosed. All right, so this is how we prove Gauss's law. So if in the examination you are asked to prove Gauss's law, you have to go through this entire part. If it is said that a single charge is enclosed by a given volume, then you can stop in the previous slide. But if it's a general statement, then and if you don't give this part, then your answer is incomplete. You won't get full marks. Okay, so you have to come to comment about the existence of several charges and go through these steps and arrive at the final expression. Okay, now, so that is so basically this is the integral form of Gauss's law. This is the most often used form of Gauss's law. When we are asked to apply Gauss's law to a charge distribution, we use this statement, but this is the integral form. There is also a differential form, which I will state and prove today. So what is the differential form of Gauss's law? This is the integral form of Gauss's law, as we saw in our previous slide. This can be converted to differential form using Gauss's divergence theorem. I hope all of you remember Gauss's divergence theorem. Remember when we were doing vector analysis, when we came across the three vector differential operators, gradient, divergence, and curl. And then when after introducing vector integration, I also stated the very, very important integration theorems, vector integration theorems, the Gauss's divergence theorem and the Stokes theorem. There is also Green's theorem, which is not a part of your syllabus, but Gauss's divergence theorem and Stokes theorem are extremely important, and I had mentioned this when we had done these in the vector analysis class. If anyone is here who has not done those classes or who is not aware of Gauss's divergence theorem or Stokes theorem, we will use Stokes theorem eventually, maybe in our next class. If you are not aware of this, then please go through the LMS notes on vector analysis that I have provided, or you can go through the videos of the recorded classes that are there on my YouTube channel where these explanations are given. But you cannot understand or go through electrostatics, study electrostatics, if you do not know Gauss's divergence theorem or Stokes theorem. These are extremely important and you need to know them. You cannot escape. So please, if you do not know, if you have missed those classes, then please go through the notes, the PowerPoint presentations that have been forwarded in the college LMS, as well as the recorded videos that are there on the YouTube channel. So please, you need to know these two theorems, okay? So what is Gauss's divergence theorem? Let's recall. Surface integral of a vector over a closed surface S is equal to volume integral of the divergence of that vector over the volume that is enclosed by that closed surface. Okay, so if you have a surface S which encloses a volume V, then Gauss's divergence theorem states that closed surface integral A dot n cap ds is equal to volume integral divergence of A dv. Okay, so you can understand that you need to know how to calculate divergence of a vector, and you need to know at least the statements of these theorems. Okay, so this is Gauss's divergence theorem. So for an electric field vector, we replace the vector A by E, because here we are dealing with the electric field vector, and we can write Gauss's divergence theorem as surface integral, closed surface integral. Again, I want you to recall that when we put a circle over the integration sign, it means that we are performing closed surface integral. The surface is closed, as in a sphere or a cube or an ellipsoid. Okay, so it's a closed surface, not an open surface. So then integration, closed surface integral E dot n cap ds is equal to volume integral divergence of E dv. Now let us suppose that the volume charge distribution is rho. Remember, we had discussed volume charge distribution, linear charge distribution, surface charge distribution in our previous class. So let us suppose that the volume charge distribution is rho. That is, we are assuming that the charge distribution is a continuous charge distribution, not discrete point charges, but it's a continuous charge distribution within the volume that is enclosed by the surface S. So we can write the total charge that is enclosed by this volume, that is capital Q. It is volume integral of rho dv. Okay, because rho is charge per unit volume, so rho is Q by V. Now V, capital V, the total volume, is basically integral dV. So we can write Q equal to integral rho dV. Okay. So we have in Gauss's law here, this is the integral form of Gauss's law. So here we can write E dot n cap ds Q by epsilon naught equal to, in place of E dot n cap ds over here, since we are considering a closed surface, I use the divergence theorem and I write integral divergence E dv. Okay, so in place of E dot n cap ds surface integral, I am writing volume integral divergence E dv using Gauss's divergence theorem. And here in the right hand side of the equation of Gauss's law, I write in place of Q, the enclosed charge, this expression of Q. Okay, I've already given you this expression of Q. So what is the new form of Gauss's law? I already know that in the integral form, Gauss's law is surface integral E dot n cap ds equal to q by epsilon naught. I use Gauss's divergence theorem to replace the surface integral by a volume integral, so that integral E dot n cap ds becomes volume integral divergence E dv, and on the right hand side I write 1 by epsilon naught volume integral rho dv, because this is the value of q, as you can see from here. Okay, so this is Gauss's law. This tells us exactly what Gauss's law tells us, but only it's in a new form that we have written utilizing the divergence theorem and the volume charge distribution. Now this relation holds for any arbitrary volume. When we started off, I did not mention any fixed volume. This was valid for any arbitrary volume. Remember, we proved Gauss's law for a volume which has any arbitrary shape. So this is true for any arbitrary volume, which enables us to equate the integrands. Since this statement is true for any arbitrary volume V, therefore the integrands, okay, the quantities that we are integrating, they must be equal. So we can write divergence of E equal to rho by epsilon naught. Okay, as you can see, divergence is a differential operator, and therefore this is the statement of Gauss's law in differential form. Clear to everybody? So Gauss's law in differential form, mathematically it is, what is it? Divergence of the electric field is equal to volume charge distribution divided by epsilon naught. In other words, the divergence of the electric field at a point is equal to the volume density of charge at that point divided by free space permeability. This is very, very important. This often comes in the exam as a question. You know what kind of a question? State Gauss's law of electrostatics. From this, derive the differential form of Gauss's law. Okay, so state the integral form of Gauss's law. From this statement, derive the differential form of Gauss's law. So this is how you will follow the steps to derive the differential form of Gauss's law from the integral form of Gauss's law. All right, I hope it is clear to everybody how these steps are to be followed. Only you have to keep in mind the expression for Gauss's divergence theorem, and as I told you before also, that is a must. You must know Gauss's divergence theorem, and you must know Stokes' theorem also, which we will require at a later time. Okay, so that is the differential form of Gauss's law. Now let us note down a few points about Gauss's law. First of all, Gauss's law follows from Coulomb's law, and it is regarded as a fundamental law of electrostatics. So just like when you were younger in school, electrostatics meant Coulomb's law. You have always related electrostatics to Coulomb's law. Force between two charges is product of the charges divided by square of the distance between the two charges. Okay, but we have to remember that Gauss's law is derived from Coulomb's law, and it is as fundamental as Coulomb's law in electrostatics. In order to find out the electric field at a point, we have to apply Gauss's law. Okay, if the surface S includes positive and negative charges, the total enclosed charge would mean the algebraic sum of all the charges. Okay, so if we are applying Gauss's law to a closed surface in which total charge is capital Q and there are discrete charges, then the total charge capital Q is the sum of all the discrete charges including their signs. Okay, you have to remember that. Whether the charges are positive or negative, that has to be considered. So you have to take the algebraic sum. For example, suppose in an enclosure we have 5 charges, okay? Plus 1, plus 2, minus 1, minus 2, plus 3. Okay? Plus 1, plus 2, minus 1, minus 2, plus 3. Then the total enclosed charge will be plus 3, because plus 1 minus 1 cancels, plus 2 minus 2 cancels, only plus 3 is left. So you have to remember that when we are talking about the total charge enclosed by a surface, we are talking about the algebraic sum of the discrete charges present if the charges are discrete. If it is a continuous distribution, then we will of course take the continuous distribution formula. But if the charges are discrete, then enclosed charge means the algebraic sum taking into account the positive or negative nature of the charges that are enclosed. The closed surface S on which Gauss's law is applied is called the Gaussian surface or the Gaussian pillbox. We'll see what this means as we do applications of Gauss's law. But Gauss's law has always to be, we have to apply it on a closed surface, because Gauss's law is applicable only for closed surface. Remember, we are applying Gauss's law when a closed surface is enclosing a certain volume. That is when we can apply Gauss's law. Alright, now we will do some applications of Gauss's law. I am exactly following the order that is given in your syllabus. Okay, the applications of Gauss's law that are mentioned in your syllabus, there are in total I think 5 or 6 applications. We will go exactly in order, in the same order in which they are mentioned in the syllabus. Okay, so when we apply Gauss's law, it means that we are basically trying to find out the electric field due to a single charge or a charge distribution at a certain point at a given distance from this charge or charge distribution. Okay, we have to remember that for applying Gauss's law, a certain symmetry is required in the problem. Although Gauss's law is applicable to any arbitrarily shaped surface, but when you are applying it practically to a situation, then only symmetric situations, symmetric geometry are applicable. So the first case is field due to a point charge. As I told you, applying Gauss's law means we are trying to find out the field due to a charge or charge distribution. So the first case that we will study, we will discuss, is the electric field due to a point charge. Okay, so let us suppose there is a point charge Q and we want to find the electric field due to this charge at a point P situated at a distance r from Q. Alright, so this is a point charge Q. I have taken this picture from the internet. So this is a point charge Q. We consider it for the time being to be positive, and we want to find, so since it is a positive point charge, so you know that electric lines of force are oriented in this manner, spreading out in all directions, spherical symmetry. So they are spreading out along the radii of a sphere surrounding this charge Q. We want to find out the electric field due to this charge at a point P, which is at a distance r from the charge Q. Now you can tell me that we already know how to do this. We know the formula for finding the electric field at a point P, which is at the distance r from Q, which is simply Q by 4 pi epsilon naught r square. Why are we doing this? This is just to show you that we did that using Coulomb's law. Remember, we found that expression of electric field into a point charge at a distance r using Coulomb's law. E equal to F equal to Q into E. So finding out how the charge Q would affect a test charge, that is, this is the source charge. So if you bring a test charge at this point P, then you apply Coulomb's law, find out the force, and we saw that we can write the force as Q into E, where E is the electric field. We'll see that the same expression can be derived using Gauss's law, which once again shows us that Gauss's law has the same fundamentality as Coulomb's law in electrostatics. Okay. So we want to find out the field at this point P, which is at a distance r from the charge Q. Now, since the electric lines of force emanate radially in all directions from the point charge, we draw a sphere of radius r passing through the point P. Okay. So we draw a sphere, imaginary sphere. Of course, this is not there. We draw it for our purpose, which has the same radius r. So it is concentric, with the spherical surfaces through which these electric lines of force pass, and it passes through the point P. Basically, this is our Gaussian surface. So the moment we draw this imaginary surface, we have a closed surface which encloses a certain volume. Everything is imaginary, but if the surface would have been there, passing through the point P, having center at the position of the charge and radius r, it would enclose a volume, and we call this our Gaussian surface. So according to Gauss's law, for this surface, we know integration E dot n cap ds is equal to q by epsilon naught, where q is the enclosed charge. Now here, this n cap is along r cap, right? Because the radii anywhere on the surface of the sphere you take ds, the normal is along the radius at that point. Anywhere you take ds, the normal is along the radius. So n cap is along r cap. The field lines are also radially outward. So the electric field is also directed along r at any point. So we can write basically E is equal to E r cap. Vector E is equal to magnitude of E into r cap. So both the normal n cap and the field E are along the same direction, that is in the radial direction. Please let me know if you don't understand any point. Okay. So now we can write in this equation integration E dot n cap ds equal to q by epsilon naught we had. So there we write vector E as E r cap and n cap ds as r cap ds. So r cap dot r cap is 1, r cap is unit vector. So dot product of two same unit vectors is 1. So that is equal to q by epsilon naught. So basically E comes out of the integration. So E integration ds equal to q by epsilon naught. Clear? E is a constant because r has the same value all over this surface. We are trying to find out E on this surface. This point P can be anywhere on the surface of this sphere. So E integration ds is equal to q by epsilon naught. But this ds, integration ds, is basically the total surface of this sphere that we have drawn. So integration ds is the surface area of the sphere of radius r, which is equal to 4 pi r square. Alright. Surface area of a sphere is 4 pi r square. So we have in this expression E into 4 pi r square equal to q by epsilon naught, so that E is q by 4 pi epsilon naught r square. Okay. So this is the expression we all know to be the expression of the electric field due to a charge q at a point P, which is at a distance r from the charge. We know this expression from Coulomb's law. Now we see we have also found the same expression by applying Gauss's law. Okay. So this is the first case that we discussed by applying Gauss's law. Okay. So the steps that you need to follow in order to apply Gauss's law to find the electric field due to a charge or a charge distribution is, first you identify the symmetry of the problem. Then you draw a Gaussian pillbox, that is a Gaussian surface, and then you apply this law, E dot n cap ds integration equal to q by epsilon naught. Okay, this is a trivial case, but as we do further examples, you will see how this is done. Example 2 is the field due to an infinite line of charge. So suppose you have a long wire, a very, very long wire, not a conducting wire, a non-conducting wire, of course, because we are talking about static electricity, so the charges cannot move. So say a very long glass rod, a thin and long glass rod, or a thin and long, plastic rod, which carries charges, static charges. Okay, so for that we have to calculate the electric field applying Gauss's law. Excuse me. This is what we are talking about. Okay, so this is a very long line of charge. By infinite line of charge, it means that these arrows show that it's a very long rod. It extends up to infinity. Now obviously in for practical purposes, you do not get a rod or a wire or a rope or a string which is infinitely long. When we say something is infinitely long, we mean that the radius, if this is a rod, then it must have a radius, right? Even if it is a very thin wire, even if it's a very thin string, it will have a radius because it's cylindrical in shape. So when we say something is infinitely long, we mean that the radius is very, very small compared to the length. Okay, so that the length can be considered to be infinitely large. That is what we mean from practical purposes when we say something is infinitely long. It means that the radius of that rod, of that cylindrical object, is very, very small compared to the length of that object. Okay, so that you can see from here, it's very thin, so the radius is much, much lesser than the length. And these arrows, once again I repeat, these arrows mean that the rod extends beyond these limits. Okay, so I have not exactly drawn the entire rod, it extends beyond these limits. Okay, so let the radius of the charge carrying line, so this line, as I am calling it, it carries a charge. Okay, charge is distributed over it, and let us suppose that the radius of the charge carrying line is A. Okay, so basically this length over here is twice A. Radius is A, so this is the diameter, so that is twice A. So the radius is A. Now on it there is a uniform charge density lambda. Since this is a very thin, long object, we consider linear charge density. Remember linear charge density, lambda is equal to dq dl, charge per unit length. So the linear charge density, so the charge is distributed uniformly over this long object, and the uniform charge density is lambda. Okay, these are the two assumptions. Now by symmetry, since this is a cylindrical object, if it's a wire or a rod, it's cylindrical in shape. So by symmetry, we can understand that the field will be perpendicular to the axis of the cylindrical wire and directed away from it. Okay, so this is the orientation of the field lines. You have to imagine a little bit, in 3 dimensions, because it is not possible for me to draw a 3D. Of course, everything is possible nowadays. People do all kinds of animations and 3D pictures, but I am not so up to date. I don't know how to construct those things. If any one of you know how to do animations or draw 3D objects, then you can help me out in modifying this. You are welcome to help me out. I could manage only this. So you have to imagine the 3D picture, a cylinder, and from its axis, the electric field lines are moving out in all directions on a circular plane. I hope you can understand. I just wish you can understand. Okay. And everywhere. So these lines are, this is just one point from which they are coming out. So same throughout the rod. The lines from each point on the rod, since the charge is uniformly distributed, so from each point on the rod, the electric lines of force radiate out perpendicular to the axis. The axis is along this length. So the electric lines radiate out perpendicular to the axis and away from it. Okay. So I have shown three positions. These lines basically exist all throughout the length of the wire. Okay. Now we want to find the field due to this charge distribution at a point P, which is at the distance r from the axis. Okay. So suppose this is the point P. Okay, all of you can see the point P, which is at a distance r from the axis. We want to find the electric field at such a point due to this rod, okay, at a distance r from the axis of the rod. So what do we do? I told you, when you are applying Gauss's law, you first have to figure out the symmetry of the problem. Then you have to draw the imaginary Gaussian surface. In this case, since clearly the symmetry of the problem is cylindrical, the problem has a cylindrical symmetry, so we draw an imaginary cylinder which is coaxial with the charged cylinder. Okay, the cylinder that we don't know the length of this rod, it is infinitely long, but the cylinder that we draw has length L and radius R. Okay, so this is the cylinder. So we draw this imaginary cylinder which passes through the point P at which we want to find out the field. So it has radius R and it has a finite length L. This is the length, the height of the cylinder basically. Okay. This is our Gaussian surface or Gaussian pillbox. As I told you, the Gaussian surface is often also called a Gaussian pillbox because it's a closed surface, so it's all sometimes called a pillbox. People used to keep pills, medicinal pills, Oshud. They used to keep those in boxes, small cylindrical boxes, which were called pillboxes. So from that, this name came, Gaussian pillbox. So this is our Gaussian pillbox for this particular problem. Okay. So now you can see that the top and bottom surfaces of the pillbox are perpendicular to the charged cylinder. This top surface of the pillbox that we have drawn and the bottom surface of the pillbox, they are perpendicular to the axis of the cylinder. This is the axis of the cylinder and these surfaces are perpendicular. Okay. So as you can see that the field lines, this particular set of field lines, they exist on the top surface of the cylinder, and so they are tangential, right? They are tangential to the surface, and you know that tangential surfaces do not contribute to the flux, right? If the lines are tangential to the surface, it means that when you take the flux E dot A being the area, so the area vector is normal, these lines are tangential, so when you are taking the dot product, the angle is 90 degree, and in dot product we have cosine theta, so cosine 90 is 0. So there is no contribution to the flux for the lines that are tangential to the surface. Therefore, the top and bottom surface, do not contribute. Okay, outward flux through the top and bottom surface, phi top or bottom, is E dot ds, E ds cos, sorry, this won't be 0. Just a second. Just a second. It's a grave mistake. This is not 0. This will be cos 0 is 1. This is 90. Okay. So it is cos 90. So flux through the top or bottom surface is 0. There is no contribution from the top or bottom surface of this cylinder. So what do we calculate for the flux? We need to calculate the flux only through this curved surface of the cylinder. Okay. Is this part clear to everybody? Why we leave out the top and bottom surface and why we consider only the curved surface? If yes, then I'll go to the next slide. Now the outward flux through the curved surface, phi curved, is E dot ds or E dot n cap ds. Now according to Gauss's law, E dot n cap ds is q by epsilon naught. Okay, so now that you have figured out the symmetry, now that you have drawn the Gaussian surface, now the third step is applying Gauss's law. Okay, now here again n cap is r cap. For the curved surface, the direction of the area on any part of the surface is along the radius, so n cap is r cap, and the field is also radially outward, so the field is also along the direction of the field is also along r cap, so vector E is E r cap. So E dot n cap ds equal to q by epsilon naught equal to, so that gives us E, we write E r cap, n cap ds, we write r cap ds equal to q by epsilon naught. So E integral ds is q by epsilon naught. So so this part is the same as the point charge, but of course here ds is different. The surface area of the curved surface is now a cylindrical surface. Okay, so ds is the curved surface area of the cylinder of radius r and length l. So the value of the curved surface is, remember, 2 pi r into height, so 2 pi rl. Okay, the cylinder is of height l and radius r, so the area of the curved surface is 2 pi rl. So in this equation we can write E into 2 pi rl equal to q by epsilon naught. Now q is lambda into L only for that part of the cylinder. Okay. If you consider only this part of the cylinder that is enclosed by the Gaussian surface, then the total charge enclosed by this surface is the charge that is residing on this length of the infinitely long rod, right? So charge distribution is lambda, that is charge per unit length. So for a length L, total charge is lambda into L. For unit length, charge is lambda. So for a length L, charge is lambda into L. Okay. So curved surface area is 2 pi rl and charge q is lambda into L. So we have in this expression of Gauss's law, E into 2 pi rl equal to lambda L by epsilon naught. So E is equal to lambda by 2 pi epsilon naught r. Okay, provided r is greater than a, that is we are at a point P which is outside the wire. Since it is a very thin wire, so we can, safely say that the point P is outside the wire. So the radius, the distance of the point P, that is r, from the axis of the wire is greater than the radius of the wire. And in that case, when lambda is the charge distribution on the wire, then the field at any distance r from the axis. Remember, r is the distance from the axis, so you have to take perpendicular distance. So that is given by this expression. Okay, so this is the expression of the electric field for an infinitely long linear charge distribution. Okay, let's call this case 1, because there might be a situation where the wire is not so thin, that is, in this case the wire is extremely thin, A is very very small, so that the point P is always outside. But suppose the wire is not so thin, it's thick, and R is less than A, that is, we are considering a point P which is inside the wire. Let us call this case 2. So in that case, what will we do? How will we apply Gauss's law? Then the total charge Q equal to lambda L is given by the total charge, enclosed by the Gaussian pillbox of length L. So for that part of the charged wire, the total charge Q is lambda L, but in terms of volume charge distribution, it is the volume of that part of the cylinder multiplied by volume charge distribution. So pi a square L into rho, where rho is the volume charge distribution. So in this case, the charge contained within the Gaussian pillbox, we write it Q prime, because remember, P is inside the wire. So the entire of the wire is not contributing to the charge. So the new charge that is enclosed by the Gaussian surface is pi r square L into rho. Okay. So in place of rho, I write it in terms of lambda, and we get pi r square L into rho into lambda by pi a square. So now the electric field, by applying Gauss's law, is satisfying this equation, integration E dot ds equal to Q prime by epsilon naught, where Q prime is the new enclosed charge. So 2 pi RL into E is R square by A square into lambda L by epsilon naught, where I have used this expression. So now E is equal to lambda R by 2 pi epsilon naught A square. Okay, when R is less than A. So this is the expression of the electric field due to a linear charge distribution. When we are trying to calculate the electric field at a point P at a distance r from the axis, but the point P is inside the cylinder. So when the point P is outside the cylinder, this is the expression, and you can see that E goes as 1 by r. Okay, so E varies as 1 by r when we are outside the cylinder. So as you move away from the cylinder, the wire, the field decreases. It is inversely proportional to r. But inside, the field is directly proportional to r. So when you are moving from the axis towards the boundary of the wire, until you reach the boundary, the field will increase linearly with r. Okay, so when you are inside, the field increases with r. When you are outside, the field decreases with r. This property will be more pronounced when we do the application for a spherical charge distribution, but we don't have time for that today. So we'll end here. So we have done two applications of Gauss's law today, the point charge distribution and the cylindrical charge distribution. Please go through them, and in our next class we'll do some more applications of Gauss's law. We'll do the spherical charge distribution. The spherical charge distribution again has 3 to 4 sub cases, and then we have to find out the field due to an infinitely large conducting surface, and so on. So we'll do all that in our next class. So let that be it. I'll upload this part of the notes in the LMS.